My name's Tim, also known as mitxela, and today I'd like to talk about a very weird art project I did a while back. So before we start, I'll say I came up with this independently, and when I did it, I thought it was one of the best things I'd ever done, but conceptually it is very simple, and that means it's very easy to copy, and also it's quite likely somebody else might have done it before. I don't know. I did look at the time, wasn't really able to find anything quite the same. And yeah, part of the reason I kept it secret is I thought, yeah, there must be something we can do with this, but yeah, I don't know. And yeah, nowadays we've got AI-generated videos, so why bother with anything, I guess. But anyway, so I'm a bit obsessed with photography and weird cameras, and one of the projects on my to-do list from about 10 years ago was to build a digital slit-scan camera. For those who don't know, I'll just quickly explain what a slit-scan camera is. So there's a few different things referred to as slit-scan. The ending of 2001: A Space Odyssey was called slit-scan, although what they did there is a slightly different technique to what I think of as a slit-scan camera. In a conventional camera, you have a lens at the front, you have a piece of film, and you have some kind of shutter in between them. And an ideal shutter opens instantly, waits for an amount of time, and then closes instantly. And in reality, most shutters are focal plane shutters that take a finite amount of time to open, slide out of the way, and then slide back in again. And a lot of digital cameras don't bother with the shutter at all. They have an electronic shutter, and that's where you just turn the sensor on and off. But electrically, it's quite hard to do that instantly. So nearly all digital cameras have some amount of rolling shutter, where the sensor is scanned progressively, and then just as if you had a physical curtain moving in front of it. Some high-end cameras, like a Hasselblad, have a leaf shutter. So that's the shutter is inside the lens. It still doesn't move instantly, but what the film sees is effectively the image fade in and fade out, rather than wipe in, wipe out. But in a slit-scan camera, there is no shutter. Instead, we have a slit, that is a very thin opening in an opaque material, something like that, which is right in front of the film. And when you press the shutter button, the film is pulled past the slit. Something like that. So slit-scan cameras were, I think, invented to capture the endings of horse races. And here's a famous public domain slit-scan image. This is a triple dead heat, which is pretty astonishing. Slit-scan cameras were useful for race finishes, partly because you can make your image as wide as you like. You can just keep pulling the film past the slit. But the more important reason is that they don't capture a fixed moment in time. They capture a fixed moment in space. You put the camera at the finish line, and it logs who went past in what order. So if we look closely at it, the horses and the riders look pretty normal, but the background is totally blurred. And I suppose you could take a similar picture by putting a conventional camera on a dolly and riding along with them and taking a picture, but it wouldn't be as extreme as this, you know. It's almost as if those riders are the only two-dimensional shapes in a one-dimensional world. So, in my obsessive photography phase, I saw someone building a DIY slit-scan camera, and I'm afraid I don't have a link to it, but what they'd done is they'd taken an SLR with a motor drive, and they'd adapted it. And the thing that was really new and interesting at the time was they were using an Arduino to control the speed of the film. And the reason that's important is it's actually quite difficult to get the correct exposure in a slit-scan image. In a normal camera, you have to balance the aperture and the shutter speed against what we call the film speed. That's its sensitivity. But in a slit-scan camera, you need to balance, if you want the correct exposure, you have the aperture, you have the slit width, you have the film speed, as in its sensitivity, but then you also have its speed, as in the velocity you're pulling it past the slit. And you also want to balance the movement of the film against the apparent angular velocity of what you're trying to take a picture of. Yeah, if you move too fast or too slow, your horses will be squished or stretched out. So I thought, wouldn't it be great to build a digital slit-scan camera? So we take some kind of linear CCD and read out the data as fast as possible. So yeah, for a reasonable resolution, we'd want probably an FPGA, loads of RAM, and it would read it out into RAM, dump it to the SD card afterwards. Yeah, so this is doable, and I did make a start on it, but I didn't get very far. I left it on the back burner until I felt the enthusiasm. In 2018, I was building my precision clock. So that's two of my precision clocks that are synchronized to within a millisecond, or it's reading out to a centisecond. But in order to get these to work, to confirm they worked, I needed a high-speed camera. I bought one of these. This is a second-hand Sony RX100 Mark IV, and this was the first consumer-grade camera to offer 1,000 frames per second video. It's upscaled to 1080p, but it was exactly what I needed to get my clock display working. So shortly after buying it, I was thinking about my digital slit-scan camera project, and I realized this is very similar hardware to what we would need. I mean, the high-speed camera has to clock data out of the sensor incredibly quickly. So it dumps it into RAM first, and then after you've finished taking a video, it then copies it onto the SD card. And it occurred to me, what if we filmed a high-speed video, cropped it to be 1 pixel wide, and then stacked all the video frames next to each other into a 2D image? Wouldn't that be a slit-scan picture? Yeah, so I went outside, filmed a high-speed video of the cars on the road outside, and ran home, wrote a really shoddy Python script to test the idea, and the result was this. Like, oh, that's a slit-scan image. Wow, it works. So obviously the cars are a bit squished, but that's just because of the frame resolution. I didn't try at all to get them the right size. Yeah, this is, you can tell it's a real slit-scan image because the cars are all facing the same way. This is the A40, there's a central reservation. The cars on either side are driving in different directions in space, but they're all driving the same direction in time. So, yeah, the bonnet always comes before the boot unless you're reversing. So yeah, that's pretty cool. Yeah, so a slit-scan image is not like a 2D picture with a camera, conventional camera. It's more like a plot where the horizontal axis is time. Yeah, so that was my first mental leap, that if you have a high-speed camera, then you already have a digital slit-scan camera. You don't need to build anything. So I immediately went outside and filmed another video of the traffic, put it through the script. Weird. Yeah, so here I'm at an angle to the traffic, and because of the perspective, the cars are changing size. Like the bus is driving towards us, but those cars are driving away. That skinny thing in the middle is a cyclist. But because he's close to the camera, he appears to be moving quickly, and so he appears squished in this slit scan. The slower you move, the wider you become in the slit scan, and eventually, if you stop moving, you become a horizontal line. So it occurred to me, when I looked at this image, it occurred to me that we've taken a video file. We've thrown away nearly all the information in it, but there's nothing stopping us retroactively processing it again, putting the slit in a different position. So instead of cropping it to be 1 pixel wide in the middle of the frame, we could crop to the edge. So I've ran the script again. It's another slit scan. Okay, so obviously at this point, the logical next step is to wrap the script in a loop, produce every possible slit scan image out of that source video, and then play them back as an animation. Obviously, so it looked like this. I mean, it's yeah. It's so weird. I mean, there's a pedestrian that walks past. It's just like, it's just casually strolling through this bizarre environment. Yeah, it's very trippy. Yeah, it's so bizarre, but it's not bizarre. It's the road outside my house. Yeah, it so happened that the following weekend I was going to a photographic affair with a couple of my friends who were also into cameras, and I was so enthusiastic. So I said to them, oh, I've got this amazing new photographic technique. Jennifer, quickly, do a cartwheel for me. And this is the source video of Jennifer doing a cartwheel at 1,000 frames per second in St. James's Park. Yeah, you know what a cartwheel looks like. And then put it through my script. It looked like this. It looks like a cartwheel, but because her legs are moving fast, they're tiny, and then at the bottom her head stretches out as it slows down. It's so good. Then she tried to teach me to do a cartwheel. That's me attempting. It's not quite so graceful, but also you can see at the end the camera followed me, and you get a bit of coherency in the background because the camera moved. Very weird. Here's Jennifer doing another ballet maneuver. We filmed a lot of these. Amazing. Yeah, then we stood in Trafalgar Square, and I got Tom and Jennifer to walk around me in a circle, so they appear multiple times. This is filmed at 120 FPS, so we get more in. And yeah, there's just so much going on in this. It's like, look at people's legs as they walk. It's like, so as a foot goes ahead of the other, like one foot slows down, becomes really wide, and then speeds up. It's so bizarre. Here's another one, Trafalgar Square. What we can see in this one is the front of the bus is slightly darker, and the back of the bus is lighter. It's like leaving a trail of light. That's the auto-exposure of the camera, because it's like a plot of time. And yeah, there's somewhere in here there's a child that runs backwards, and they're the only thing that faces to the right. Oh, there it is. Like, oh. The sad thing is, Tom and Jennifer didn't actually see these results because my script was too slow. It was so hastily put together that, it just repeatedly decoded the video for every single frame of output. And when I got home, started to optimize the script. Of course, decode the video once and just hold it in memory and slice out the data we need. I also added options for trimming and cropping the video. If we want our output to be 1080p, that's 1920 pixels wide, so we need our source video to be at least 1920 frames. So at 120 FPS, that's like 16 seconds. If the video is longer or shorter, then it needs to be trimmed or scaled. We actually have a lot of variables. We could crop the input video to change the length of our output video. It's a bit weird. Also, we don't need to limit ourselves to a vertical slit. We could do a horizontal slit, scanned vertically. So here's the same thing again. It's not very coherent, but it's very interesting. The next video is Trafalgar Square again, vertically. And remember, the vertical axis is time. So the pedestrians start out as stripes, but then they kind of turn into double helixes because of their legs. It's just... Okay. So I was looking at this, and I think this is the moment when it clicked what I was doing. So if we take one of these outputs and run the script on it again, it gives us back the original video file. The process is its own inverse. Stick with me on this. If we think of our video as a four-dimensional matrix, then there's a mathematical term for what we've done here. We have transposed the time and space coordinates. And yeah, I went up to my friends. This is just another one. I was like, picture a scene as a four-dimensional matrix and transpose the time and space coordinates. This is incredible. And they all thought I was crazy. We always knew he was a bit weird, but now he's really lost the plot. So what I needed to explain the process was a diagram. So I turned to my favorite bit of software in the world, Blender. Yeah, so if we ask FFmpeg to give us the video as a raw stream of bytes, the first 3 bytes it gives us are RGB of the first pixel. That is our first dimension. The next 3 bytes represent the next pixel, and so on until we've got a line you can just about see there. This is the second dimension of our array, and then when it gets to the end of the line, it starts on the next one immediately, and it carries on until we've got a whole frame. This is the third dimension of our array. At the end of the frame, it immediately starts on the next frame, our fourth dimension. And if we stack these frames together, we can construct a data cube. Oh, look at that. Yeah, and all our script is doing is playing it back in a different direction. So yeah, just to get the most out of this animation, oh, thank you, yeah. Tab out for a moment. Oh yeah, here we are. This is the Blender file. I'll just play it here. So, oh, I loved Blender. I made this in Blender 2.79. Just opened it like the other day. It still works. Didn't even complain. This is Blender 5. And yeah, you can see her legs striping the top there. And yeah, the camera shake is really, you can see how the stripes in the image are, yeah, just camera shake. Yeah, it should start playing again in a moment. Whoa. Amazing. So yeah, I had a lot of fun making that animation. Yeah, Blender can't preview it quite at full speed, but well, there we go. Right, where were we in our? Yeah. Right, we were here, I think. Yeah. So yeah, it was probably a few months between me realizing that yeah, it's a transpose and actually getting around to making this animation. One of the things I tried to do was come up with a name for the effect. Maybe something in Greek that would describe transposing time and space, but everything I tried to think of turned out to already be a name for something else. So I ended up calling it the Xelatype, as you might have guessed. Yeah, I did also see, I had a quick look to see if anyone else had done this, because like once you've seen that animation, it's actually, well, it's kind of easy, right? There's nothing to it once you've seen that. And at the time, I couldn't find anyone else who'd done quite the same thing. There is an effect in After Effects called slit-scan, but it's not slit-scan, it's rolling shutter. So what they're doing is progressively delaying different parts of the image, which is a valid artistic effect. It looks cool, but it's not transposing time and space. So if you think of the data cube, it's like it's turned into a parallelogram, but then played back in the same direction. With our script, the next step, as far as I was concerned, was to rewrite it, now armed with the knowledge of what's going on. I did produce a little program in C, which shuffles the bytes for us, but it's not particularly clear what's going on here. I mean, you pipe FFmpeg straight into this, pipe it back into FFmpeg to re-encode the video, but you wouldn't look at that and say, ah, yes, it's a transpose. And also, it's not actually that efficient, because we're dealing with lots of bytes here. It's 1920 frames at 1080p is about 11 gigabytes uncompressed. So there's definitely better ways to handle this sort of thing. So what I wanted to do was use NumPy, the Python library, and tell it at a high level what we want to do. So yeah, because even though Python is high level, but a lot of NumPy is optimized very well. It's compiled, and it's very good for big transforms. The core of our operation looked like this. So NumPy video in into an ND array, and then just NumPy transpose. As I understand it, NumPy transpose only affects the view you have on the data. It doesn't do any shuffling until you make use of it or write it to disk. If we want to be really clever, we could think about how the data chunks are being shuffled about, because a vertical slit is a sparse collection of pixels, but a horizontal slit corresponds to a scan line. So if we rotate our video before we do the transpose and then rotate it back, it'll be much more efficient. yeah, and rotating the video, you can just do that in FFmpeg. You just pass it a filter, and because it's got access to hardware acceleration, it's very, very fast. If you get the logic slightly wrong, it vomits out nonsense. Here's some nonsense. Even looks like vomit. I'll admit that some of the optimization is a bit pointless, because even at this point, the old script was taking about a minute to run. But for demonstration purposes, I wanted to make a version of my script as short as possible. I did get it down to about 4 lines of Python, but because you need to give all these arguments to FFmpeg, it's somewhat unavoidable. So it did end up looking a bit of a mess, and I'm not sure if anyone can even read that here, but I've added white space to try and make it clear. If you ignore all of the FFmpeg subprocess stuff, it is just video in, ND array, transpose, write it out as bytes again. And yeah, of course, all of the parameters are hard-coded, so what I wanted to do next was go back to my original script, rewrite it to use this clear and fast way of doing the transpose, but then keep all of the options I'd added for the different modes and features. But yeah, I got distracted halfway through. Most of the source code was left in a state that's not really fit to publish yet, but I will put it up on GitHub at some point after this talk. I also described the process to my other friend, Tom, who, yeah, I showed him some of the results, and he had a go at making his own script for it, which I've got, but yeah, he took a slightly different approach. Yeah, but so conceptually, what I wanted to do next with this was explore different transformations of the data cube, because everything we've done has been a 90-degree rotation, but what if we did a 45-degree rotation and played that back? I mean, you'd get some kind of hybrid result. I'm sure there's a lot of experimentation that could be done here. Yeah, now that we've got this kind of mental picture of the video. So, yeah, to finish up, I've got a load more of these examples, because I've made a lot of them. So, yeah, I'll just go through them. So that's Jennifer doing another cartwheel. Then we've got, what's this one going to be? Oh, it's me doing a roly-poly. Then we've got me jumping up and down, I think. Yeah, so because I'm going up and down, it looks like a weird sine wave. And we've got, yeah, more traffic. This is the level crossing outside Axon Central. So you can see the gates going up and down, train goes through, all these people waiting. Very weird. This is a mini roundabout. I've got a lot of traffic. It always looks weird. Yeah, you pay attention to the wheels of the cars. They're just so strange. This is a fairground that was nearby. So these are like, it's a carousel. It's very odd. We've also got there's some vertical bands when the lights go past. That's the 50 hertz frequency flicker. Yeah, there's more of the fairground. In this one, you've got passengers on the carousel who appear in 2 places and then merge with themselves. Oh, oh. And then some people walk past. Yeah, again, you can see the 50 hertz pulsing of the lights. Yeah, another one. I must have rocked the camera there because it's going up and down. This is my friend's cat. It's quite difficult to capture a cat because, yeah, it's difficult to get them to run past on cue. There's a cat again, chasing her, trying to entice it past the camera. and it just disappears. This is a view out of a train window. So it's very similar to that other talk that was on Friday by Philomena Gray. What you end up with is essentially a normal picture, what with this weird perspective stuff, and again, the 50 hertz pulsing there. Yeah, this is the view out of a bus, just driving past some trees and some cars. Because of whatever frame rate I used, it's squished them all together into this weird thing. There's a double yellow line. Here's another one of my friends on a kid's roundabout. It's being spun, and there's a person spinning them. Another one of Jennifer doing another ballet thing. This is Crossness Pumping Station. This is a steam engine, and it's scanned vertically. It's very odd. In this one, I put the camera on a gimbal, a motorized gimbal that rotated it with a wide-angle lens, so the background looks coherent, but it's still slit scan, and yeah, you can see those bands where the auto exposure of the camera is, dimming it as the white vans go past. And another similar one. I think I must have started static and then started panning the camera. It's very weird. More traffic. Some ambulances. I'm guessing that was a railing in the foreground. Yes, I've got lots of these. What's next? Yeah, this one has a cyclist going up the hill, and then a pedestrian walks past, but for some reason it looks like she's hopping. I'm not sure what effect that was, but and yeah, just finally, this one, having not done this for many years, just earlier today, about an hour ago, I thought I'd do an EMF one, so this is me pulling World of Techno past the EMF sign. Yeah, so that's pretty much the Xelatype. I've got the camera with me, so if anyone feels inspired and would like to pose or has an interesting idea, we could do some of these later today if you like. I guess, and that's it.